Okay. So you know that as Richard Feynman once said, the best way to learn physics or to learn something is that after you learn it, you re-speak it, you speak it out as if you are teaching others what you have learned. And in this way, you can learn the things better. So let's try this method. And today we start with the quantum mechanics. So this part is based on Griffith's quantum mechanics from chapter 1, from 1.1 to 1.4. So you know that in classical mechanics, when what we want is that we want to find the position of a particle as a function of time, namely xt. So after we find xt, we can find a lot of things. For instance, the velocity, which is dx dt, the momentum, which is mv, and the kinetic energy, which is 1 over 2 mv squared. And we can find all the dynamical things of our interest. So how are we supposed to get xt? We get it by the Newton's second law, right? So we know that F equals ma equals m dx squared dt squared. So from Newton's second law, we can get the xt. And by the way, like if the force is conservative, we also know that the first is just the gradient of the potential, right? So together, we can determine the position of the particle as a function of time. This is what we did in the classical mechanics. Okay, now we are talking about quantum mechanics, and quantum mechanics doing the things in a similar way, but like in quite different way. But they eventually want to find a similar thing because in quantum mechanics we want to find a thing called wave function, which we call it phi x of t. I guess like you are not unfamiliar with this wave function because we have already seen it in the ENM, right? ENM, right? It's the electric and magnetic wave. So how do we get the waves equation? Well, we solve it by the Schrödinger's equation, which is I h bar d phi dt equals minus h bar squared over 2m. Okay, this is the Schrödinger's equation. So Schrödinger equation works exactly as the same, not exactly I should say, but it's similar to Newton's second law in the classical mechanic. I give you a initial condition, for instance, like phi x 0. And so Schrödinger equations will predict the phi xt for later time, right? So it's just to point out that here the h bar is the Planck's constant over 2n. Oh, sorry, it's over 2 pi. Okay, so this is Griffith's 1.1. It introduces the wave equation and it somehow links the quantum mechanics to the classical mechanics. In quantum mechanics, we want to find the wave function. Okay, so but what exactly is this like wave function? So like in ENM, we know that wave function somehow contributes to EM waves, but what about in quantum mechanics? So, well, according to Born's statistical interpretation of this wave function, the wave function gives the probability, I should say the square of the magnitude of the wave function gives the probability of finding the particle at a point x or time t. Or more precisely, let me write this. The integral of a to b of the magnitude of phi xt squared dx equals the probability of finding the particle between a and b at time t. So as we know, like for this is an integral, right? So probability is just the area under the graph of phi absolute value squared. So this statistical interpretation introduces some kind of indeterminacy into quantum mechanics because everything you know is probability, right? You don't have a absolute thing in quantum mechanics. All the things you get is based on probability, which is the integral of the phi squared, right? And so this is really, I mean, fantastic and non-intuitive. And when I was very young, first read about these things, I was totally shocked. I mean, like, how, oh my God, how can the world based on the probability, right? So so now here's the problem. So when I do a measure of the particle that I found to be at point C, the question is, where is it after I make the where was it before I make the measurement? So there are several assumptions. The first assumption is called the realistic assumption. Well, and this one is advocated by Einstein. While the realists say that, of course, the particle was at C before you measure it, and like you measure it, it didn't change. It's still at the position C, because the realists don't accept something as ridiculous as the indeterminacy. As so, somebody put out that the position of the particle was never indeterminable, but was merely unknown to the experimenter, and they suggest that the phi, the wave function, it doesn't tell the whole story about a particle. I mean, there are some additional information, hidden variable, that is needed to give a complete description of the particle. So it is not that you don't know it is only that like you don't know the previous state of particle, but that particle must be also at point C before you make an observation. And next is the orthodox position, which we know from now under the efforts of many people that this is the correct one. So this position said that the particle isn't really anywhere. Like the moment we make a measurement, it collapses to this state. But before we do the measurement, before we do any observation, the particle is simply not anywhere. And as Jordan said, the observation not only disturb what is to be measured, but they produce it. And this view is called the Copenhagen interpretation. It's supported by Bohr and other physicists. And I think it's really amazing for these people to come up with such thing. And finally, it's called the angoistic position. And this position kind of refuses to answer the problem because they think that this is kind of meaningless to ask this problem, because the only way you get to know the position of a particle or of something is that you do a measurement. So what is the meaning to ask that what is position before this measurement if the only thing to make sure its position is to do the measurement, right? And this is like the theory that be supported by physics, that is Pauli. Pauli said one should know more wreck one's brain about the problem whether something one cannot know anything about exists as the same. About the ancient question of how many angels are able to sit on the point of a needle. But this thing has unfortunately like been be refused or be proven wrong by a physicist called John Bell. I think we will mention John Bell again in the very later to like for further information. But like John Bell has proved that okay, this particle before our measurement do have a precise precision. Although we don't know it, but it do have a precise precision. So this angonistic precision doesn't stand anymore. So I hope that one day we can go back to Joe Bell's statement that we know the position, they do have a position. It's only that we don't know in the future. But I guess it will be a long story. So let's just continue with our discussion. So I just said that actually the first measurement radically alters the wave function. So it's now sharpened. So the probability function is now sharpened at point C, which means that the point C has almost all the, has all the possibility, and the wave function collapses to a spike at the point C. So, but like after we don't measure it, it will spread out again, according to the Schrödinger's equation. So there are actually two physical processes goes on here. The ordinary one, in which we don't do the measurement, we don't do the observation, and the wave function is controlled by the Schrödinger's equation. and the measurement in which the wave function phi suddenly collapsed discontinuously into a spike. And this is Griffith's 1.2. It talks about the Schrödinger's equation, like the probability, and they cause the indeterminacy. Some views about the indeterminacy and like the collapse, like when we do the observation, the probability function collapse. Okay, now let's continue. So before we do anything about the quantum mechanics further, we need to talk about probability, right? Because this is an important part about quantum mechanics, as we just said, that's the probability theory. I should say that the quantum theory is based on probability. So let's see some kind of equations for quantum mechanics. So definitely like the total probability is added. So n equals nj from j equals 0 to infinity, and the probability of finding one case is nj over n, right? And then let's see. Yes, so the probability, all the probability should add from 0 to add to 1, because you always get like 100% probability, right? And the average is just the j and j times n, which is j times pj. No, this is important. It means that the sum of each cases times their probability is the average case. And okay, and actually the average matters a lot in the quantum mechanics, and we call the average sometimes called to be the expectation value. And so as for j squared, oh my god, for j squared, we can call it the average. So this is the average of, let me write it as this. And from this, we see a pattern. The average of any function related to j is the function times the probability of j, and add them together. And we also want not only we want to know about the average, but we also want to know about the division, because only like the average doesn't tell the division. Like for instance, this probability function and this probability function may have the same average, but their division is definitely different. So we want a way to measure the division, and actually we want to measure delta j, which is j minus the average of j. Like we want to measure how much each value of j is different from its median. But the trouble is that this thing is actually the average of this thing is 0, because, well, some like the above average, the values are greater, below the average, the values are less. So they somehow counter each other. And so the value is 0. And actually we want it to be the absolute value, or if we don't want to have trouble with the sign, we want to know that the average, the value of the delta j squared, and this can solve this issue. And there's a nice way to calculate the average of delta j squared, which we call it the variance. It's just the average of j squared minus j, the average of j squared. And the standard deviation is just the square root of this. Okay, it's pretty cool. And this is the discrete case, right? And we could easily apply the same thing to the continuous situation. As long so if we say like we replace px with rho x, which is the probability density, and the probability of getting something at point AB is just the integral of AB rho x dx. And I guess you know that the probability to get fx is just you times fx with fx rho x dx, and this is the continuous probability theory. Okay, finally, today's last topic is about normalization. We see that the integral of the phi square must be 1. Let me write it. The integral of phi squared must be 1. Because the particle has to exist, right? It can't just disappear. So like if we integrate all over the interval, we definitely at some places will find this particle. But we remember that phi is dependent by the Schrödinger's equation. So how will the Schrödinger assure us that this equation indeed holds in the Schrödinger's equation? Well, you may have noticed that the Schrödinger's equation is a linear equation. So actually, if phi xt is the solution to the Schrödinger's equation, then a phi of xt is also a solution to Schrödinger's equation if a is a constant. So which means that if we find the phi xt, we need to normalize it, turn it into a x phi of t in order for this equation to hold. And this is the normalization of the Schrödinger's equation. And it's a very interesting question. So suppose I normalized the wave function, but how do I know that when time progresses, this wave function is still normalized? Isn't it like how do you prove that? And there's a proving provided in Griffiths' book, which I don't want to go deep further, but it finally shows us that the normalized solution keeps normalized when the time process. And this is the Griffiths 1.1 to 1.4. Okay, so we'll talk about more things tomorrow.